Thank you for the introduction. For those who don't know me, I'm a PhD student working with Jingyu. So I'm going to talk about a fundamental issue, that is the sea surface drag coefficient. So here's the outline. So after the introduction, I will show the analysis of observational data and application to the surface wave simulations. Brief summary will be in the end. So estimation of wind stress is needed for the numerical modeling of ocean and atmospheric dynamics. So this animation for NOAA shows the evolution of ocean surface gravitative waves, which are caused by wind, and wind stress acting on the ocean surface are important for the wave evolution, not only in the deep water, but also in shallow waters. So wind stress is also the primary driving forcing for ocean currents and many other phenomena such as storm surges. So this animation shows the ocean surface currents. And you can see the Gulf Stream here propagating of ocean surface currents. So the fundamental issue is, how do we calculate the wind stress? So I guess most of you have the answer. So wind stress is normally estimated from the wind speed using a Buckle formula in terms of drag coefficient. And the drag coefficient is usually considered as a function of the wind speed. And it can be related with the sea surface roughness under neutral conditions. So, however, the wind stress or the drag coefficient is not only determined by the wind shear from the wind speed, but also the pressure fluctuation caused due to the surface waves, and also the viscosity shear. Although the last one is only important in a thin layer, and it's usually small. So in other words, the sea surface roughness can be decomposed into a smooth flow component due to viscosity and a rough flow component driven by the winds and the waves. So the question is, how do we consider the effect of ocean surface waves on wind stress? So here, the wave effect on the drag coefficient can be included by taking the non-dimensional roughness. You can see here several different kinds of non-dimensional roughness. It can be considered as a function of wave age or wave steepness. So here in these formulas, M1, M2, N1, N2, and A1, A2, these are empirical parameters determined using observational data. So the wave steepness is the ratio of significant wave height over the peak wavelength, which is a geometric parameter measuring the wave nonlinearity. And the wave age, which is the ratio of wave phase speed over the frictional velocity, so which determine the ability of momentum transfer. So you can see from these figures, so young waves and the steep waves may have support larger wind stress. However, these formulas are quite different from each other, as suggested. These formulas suggested in previous studies. So, in other words, the inclusion of wave effects on the wind stress still have large uncertainties, and that brings up the objectives of this study. The first one is to examine the dependencies of drag coefficient on the wind speed and the sea state. And based on these understandings, the more important one is to develop a new wave-dependent scheme for the drag coefficient, which can well represent the wind stress at the sea surface under different sea states. And the method used here, we first analyze the observational data from field experiment, and then assess the different schemes for the drag coefficient using a nested grid ocean surface wave model for the Northwest Atlantic. So here we first summarize the observational wind stress and the wave data from 8 field experiments. These data were collected in previous studies under a wide range of wind and wave conditions. And this figure here shows the drag coefficient as a function of wind speed using these data. So the gray dots represent data under wind wave dominated conditions, and the cross represent data under swell dominated conditions. And those black dots represent the being averaged values of the observed drag coefficient. So one of the important features for this figure is that the drag coefficient has larger values for lower wind speed at low winds. So this is consistent with previous studies in Yellen and Taylor and also Wei. And this is mostly due to the wind gustiness at low winds. Although the mean wind speed is low, but the fluctuation can sometimes be large. And also those swell propagating in the opposite direction of the wind can also contribute to this kind of enhanced drag coefficient at low winds. So however, the widely used schemes such as Largent Palm and Huan, they do not represent the enhanced drag coefficient at low winds. And at moderate winds, Largent Palm, indicated by the blue line here, underestimate the mean values of the observed drag coefficient. And Huan's formula, indicated by the red line, shows some overestimations. So we are going to talk about this later. So as we mentioned above, the wave-dependent drag coefficient is usually described by the non-dimensional roughness as a function of a wave steepness or wave age. Here we show the calculated values of the non-dimensional roughness using observational data in terms of the wave steepness and inverse wave age. We can see that the non-dimensional roughness has stronger correlation in comparison between these two different variables. So in other words, it has strong correlation with inverse wave age. And for the comparison between data and the previous formulas, the blue line, you can see here, the blue line will represent the observed values for young waves. And the magenta lines may have good agreement for older waves. And it's similar in panel D. This indicates the relationships between non-dimensional roughness and the wave age may not be unique, but can be different under different sea states. So if we also consider the data under swell-dominated sea states, we can find that the existing formulas hardly follow those data, particularly for swell-dominated sea conditions. But on average, the observed values are generally larger for older waves under the swell-dominated sea conditions, which corresponds to the enhanced drag coefficient at low winds, as we just mentioned in previous slides. So therefore, we argue that the relationship between the non-dimensional roughness and the wave age are not unique, but vary under different sea states. So we have the following regression here that the parameters N1, N2, they are not constants, but 3 pairs of different values under 3 different sea states. So for now, we then have a look at the calculated drag coefficient using different schemes in terms of the wind speed, wave age, and significant wave height. The color represents the value of drag coefficient. So in previous schemes, the left 4 panels, so we can see young waves and larger waves would have larger values of drag coefficient. Okay, by comparison, the important feature of the new scheme in panel F, so is that the new scheme based on this equation 11 is the only one to have the enhanced drag coefficient at low winds. And then we then compare the observed values of friction velocity with the predict values using different schemes. And for error metrics are introduced to quantify the performances. So which are relative by rooming square error, scatter index, and correlation coefficient. So the wing speed formula suggested by Lard and Palm, they have a larger negative bias, which indicates systematically underestimation of a friction velocity. And the Huang's formula overall have slightly positive relative bias due to the overestimations at moderate wings, as we mentioned in previous. So in comparison with other schemes, the new scheme here, and also indicated by the red cross in this scatter plot, you can see loss data spread closer to the perfect fitting line, and the areas for this scheme is much smaller than others. So the reason for the good performance is that it shows the effect of wave effect, a wave on the drag coefficient. And then to further assess the performance of different schemes for the drag coefficient, so we have several different schemes are implemented into a nested grid ocean surface wave model for the Northwest Atlantic. So based on wave model, Wave-watch 3. So the smaller one, you can see from this figure, the smaller one is the outer model domain covering the entire North Atlantic at 1/4 degree. And the inner model covers the Northwest Atlantic at 1/12 degree. So the wave field during the winter storm, known as March 2014 nor'easter, are simulated using the wind forcing from CFSR. And we also consider the effect of currents by using HICON data, and effect of sea ice by using Canadian ice surface data. And the observations from the in-situ buoy data and the satellite altimeter data are used here in the assessment. And I should mention, we implemented 4 different schemes for the calculation of wind stress or the drag coefficient. So the lower panel shows the sea ice. You can see the large scale winter storm forcing spreading over this region. And from the current, you can see the Gulf Stream. And for the sea ice mostly occurred over the Labrador Shelf and in the Gulf St. Lawrence. So we now have a look at the model results. So the use of different schemes leads to different wind stress acting on the ocean surface and thus different sea states. So this figure shows the snapshot of friction velocity and significant wave height under the strong winter storm forcing. So in comparison with panel C and D, the first 2 panels, so which are wave-dependent schemes suggested in previous studies. So they have larger friction velocity at high winds, but lower friction velocity at low winds. So if we compare the model results with observation, so you can see here the observed significant wave height from the satellite data are overlaid in the second column. So we can see the significant wave height are overestimated at high winds in panels A and B. And the Huang's formula has the problem for the overestimation at moderate winds. And the new formula, so if we compare the model result with all available observational data from buoys and altimeters, in terms of the scatter plot, we can see for the first two schemes, we can see the estimation of significant wave height at high winds, and larger underestimation for the low values. So overall, the model results have larger negative bias, which can be more than 30%. And for Huang's formula, which is the default one used with three combined with this source term. So you can see it has reasonable performance, but the new formula have better performance with data spread closer to the ideal fit, the perfect fitting line. So this is attributed to that the new scheme has more accurate predictions of drag coefficient, because it takes account of different dependency at different sea states, and not only on the wave age, but also on significant wave height. So if we compare the being averaged relative bias of significant wave height in terms of wind speed and wave age, we can see very different performance for these four different schemes. This is actually, as we just mentioned, due to the different calculated wind stress acting on the ocean surface. So if we calculate the drag coefficient from the model output, you can see the new scheme is the only one can represent the enhanced drag coefficient at low winds. And the new scheme has slightly lower values of drag coefficient compared with the default one, Huang's formula indicated by the magenta line. So that's the reason why the new scheme can reduce the underestimations at low winds and the overestimation at moderate and high winds, as compared with the default formula, Huang's formula. And it is similar for the different sea states. As you can see from the right panel, it can reduce the underestimation for old waves and the overestimation for young waves. So let's we show how the new scheme can well represent the sea state and can have good performance in the model simulations. So what's the take-home message? So from the analysis of observational data, we show different dependencies of the non-dimensional sea surface roughness on the wave age under different sea states. And that's the most important feature for the new scheme. And the new scheme shows the dependency of drag coefficient on the wave age, wind speed, and also the significant wave height. And overall, the drag coefficient predicted by the new scheme, it first decreases with wind speed at low winds, and then gradually increases with wind speed at moderate winds until it levels off at high winds. So the leveling of at high winds is due to the dependency on significant wave height, which is naturally saturated at high winds. So that this new scheme is still not perfect, but as we just showed in the assessment, we show the new scheme can well represent the observational data from field experiment and also reduce the errors for the existing scheme for in the numerical modeling of ocean surface waves. And for more details, so I discussed in our paper published in recently in Continental Shelf Research. And that's pretty much for my talk.
Okay, great. Does anyone else
take any questions?
Questions? I see Christoph has a question.
Yeah. Hi, Shangfei. Nice talk. I was just wondering, so you tested your model that was coupled to wave model. What if I don't have a wave model? And I think on your second last slide, you had sort of a function for your drag coefficient. What if you have you tried anything to plug that into a normal ocean model without wave model and see the effect of that, basically, trying to if it does any improvement on the model statistics?
Yes, that's a good question. So because this formula would require the information on the ocean surface waves, so if we want to use the new formula, we have to have information for the ocean surface waves. At least we should have a wave age or wave and the wave height for this formula. So in order, if we really want to use this one, there are two ways. One way is we should use a coupled model to provide the wave information. But another easier way is to find some wave analysis, wave overlay analysis data. I think they can provide some kind of wave information, and use those information, we can calculate the wind shears acting on the general circulation model. Does that answer your question?
Yeah, kind of. Okay, thank you.
Thank you.
Anyone else have any questions out there? Will?
Hi. On this slide number 6, it's interesting, the comparison between the altimeter data and the wave data. Don't you think the altimeter data looks a bit, slide number 6 or 10, I guess that's 10.
Yeah, I guess
don't you
it's
think
10.
the altimeter data looks a little smooth? And so I was just wondering, are there any biases in the altimeter data? You have the buoy data, so if you had an overpass of altimeter and buoy, you could just do a check to see if these two data sets are consistent, if there are any biases in the high waves for the altimeter data. It would be something you could just, check. What do you think? Do you find this altimeter track looks a little smooth to you in this plot?
Yeah, it could be. That's a good point. Yeah, probably. I can double check the altimeter data with buoy data, but I think
it should be good, because after all, a lot of people use this data. But I just wonder if it is, and so it's something you can easily check because you have both the data from both buoy and altimeter.
yes. Thank you for your suggestion. Yeah.
Okay, well, thanks a lot, Shangfei, for the talk. Very interesting.